Welcome to Basic Wave Polarization. This is our introduction to polarization. We're going to look at linear polarization. This is a characteristic of waves that's really important in optics and what we are going to do later in the course. So this is the basics. Let's start with the simplest case of a wave traveling in the z direction with the electric field only having an x component. It has an amplitude. It has this factor, which these two would give us our phasor solution. We want to put it in time, so we have e to the j omega t. We take the real part, and we have a single e component, and we know this. This is our famous formula t minus z over c if we divide out the omega. Its amplitude is this, and x hat direction. The h that accompanies it has the same form. Its amplitude is given by Ex divided by the intrinsic impedance, and it's in the y direction. Now, let's look at a snapshot of this wave at fixed z equals 0 for 3 values of omega t. So let's start at omega t equals to 0. In that case, we see that z is 0, so this is maximum value of cosine. So let's say it's this. Here is my E field in the x direction only. Now the h is the same, except it's divided by something that's positive, so it'll be a little smaller. So there it is. There's h. So that's a snapshot of our wave at a particular z. To make it easy, we're putting z equals 0, and that's the vector values of our wave. And this, of course, is at time 0. Now, what we want to see is what happens as omega t changes at that fixed value of z. So let's take another value of z.
Oh, before that, which direction is the wave traveling?
That's a good question. So which direction is the wave traveling? X cross y is z. So that's out of the board. And out of the board, as you are in the camera, is this way. So I'm sticking the pen out that way. The pen is, I can turn it at a slight angle. So it's the point of the pen. Now let's see, if I put it that way, that's the wrong direction. So the point is sticking out of the board, and
so it's out of the page but towards the camera, right? So I think what they will be seeing is the arrowhead.
Yeah, you're going to be seeing the arrowhead coming out of the page. Thank you. That's a good way of doing it. That's where the wave is coming. It's coming out of the page and normal to the xy plane. So that's going to be the same in all these examples. Now, let's take omega t equals pi over 3.
So 60 degrees.
What's cosine of 60 degrees?
Huh. That one's an easy one. Is it 1/2?
1/2. So now, at this time, omega t equals pi over 3. That t would be pi over 3 omega. At that time, the e value is 1/2. And, of course, the h value is 1/2 of what it was. So that's that. So there's my e. Let's put h up here. And this is h. And this is e. Oh, boy. And now, the easy one. Omega t equals pi over 2. So cosine of pi over 2.
I think it's 0.
So that's easy. They're right here. So Ex equals, in value, is going to be 0 times x hat. And h is going to be 0 times y hat. It's not correct to say E equals 0 because E is a vector. and 0 is a number. So you have to, I know it sounds silly, but if you say E is equal to 0, that's not correct. You would have to say the magnitude of E is equals to 0 if you were just talking about magnitudes. So if we want magnitudes only, we can do it like this. And we put magnitudes. That's it. So the magnitude of those two is equal to 0. Now, what's going to happen if we go, Sam, if we go past omega t is equal to pi over 2? What would the next picture in this series look like?
Well, following the trend, it reduced towards 0 as time progressed. So it will just go the other direction?
Yeah, because cosine of anything between 0 and between pi over 2 and 3 pi over 2 is negative. So cosine, the next picture would be a little bit of negative cosine and a little bit of negative sine, the y-axis, and so on. So fully negative, fully negative. So that means that the picture that we have is that if we look at it as a movie, h will go up and down along the y-axis, and E will go back and forth. So you can think of it like a vibrating mass on a spring in two perpendicular directions.
That's
so
beautiful.
Now, let's make it more interesting because we only had E in the x direction. So I'll leave it to you, Sam, and you can ask me questions.
Okay, I'll ask a lot of questions. What do you want me to do?
Well, I want you to make it more interesting. Let's add another component to E.
Let's do that. Throw in an EY for free.
An EY.
So E to the j omega t, E to the negative j beta z.
What's the Z, the H going to be?
Well, it started off like that. Now I added a y component to the E, so that h has to be a negative x component.
Negative x component, right. So when you take the cross product, the energy is still in the positive Z direction.
Exactly. Negative EY over eta, E j omega t, E negative j beta z.
Great.
Great.
Oh, now we want to fix this up, right? Because now you have a vector with two components, so we need to add stuff here, right small, plus.
Sounds good. So we add E, Y, cos, well, it's the same thing. And then in the y direction.
Right?
Then for h, we have minus E, Y over eta.
We're going to have a picture here.
Oh, right.
So here,
Let's offset it a little.
let's move it over a bit, because otherwise we won't have room for the great artistic Leonardo da Vinci's here.
Straight lines. Y over eta, cos, same thing, and then in the direction of x.
All right, the pictures now.
Sounds good. Let's say we have some significant x component and just add some small y component
Okay.
for the e. So that's ex, some small ey.
Now those are still vectors. So when we write EX like this isn't the amplitude, right? We want to actually somehow indicate that's the x component of E. So that's what we're doing in the y component. So now what's the net component going to look like?
So you add them together and you get that. So that's E.
Now let's see if we can use a different color. Orange is good. for H. I'll be the H handler. You can draw the H now.
So it's just 90 degree there, and then we draw it a bit smaller due to the eta factor.
Right?
So, well, it's actually going to run into the EY. Do we want to draw this better?
Yeah, let's redraw it. Maybe you can label it as EY in the,
On the right side.
on the right side, yeah. And then we won't keep labeling it, it'll be clear.
Yep. EY there.
And there's your, yeah, you got it?
And
Oh,
then
you want to give that to
H.
me? That's H. Great.
And it's a right angle. Well, I won't draw the
We
right
won't draw
angle.
the right angle.
Yep.
We know that this angle between here and here is 90 degrees. Now, I'll give you back the green one. And we're doing at omega t is equal to pi over 3. So what's going to happen?
Well, just like before, except we now have an extra component. So the x component of E would be halved, and the y component of E would be halved. So E total would just be halved.
Right. And what about H?
H would also be halved.
Okay, so you want to draw those in? You draw the
Sure.
E?
I guess I'll not draw the components.
No,
That's
now
clear enough.
just put E. That's the E total. That's just E. Right. And now the H, about a half. And now the easy one. Since you got H in hand already, you can draw it. What's the magnitude of H?
Oh. Here or here?
Yeah, here, right here.
0.
For both of them. So we don't, you may want to write that the magnitudes are 0. Magnitude of E equals magnitude 0, and same for H.
Actually, the real part of the magnitude, right?
Well, we're
Well, since we're
already
taking-
here. No,
yeah,
no, we're
we're
already
taking
here.
cosine,
So
so-
we're,
yep.
we're fine.
That's fine.
Omega t will be 0 when omega t is pi over 2, z is 0, so that's cosine pi over 2, and these are all real the way we've done it, so that's okay. And
That's great.
Sam, what will happen when we go past omega t equals pi over 2?
So it just keeps going that way again, and you get this sort of oscillation for E,
Right.
and that sort of oscillation for H.
Right, and notice that the oscillations will be in phase because these are in phase. Now, what we want to do in the next presentation is think what happens if one of the components is out of phase by 90 degrees. Will we still get linear polarization? Do you have any guesses
Wow.
about that?
Huh.
Just a guess, don't.
Well, the way you set this question up, I guess it will be different.
Okay, let's find out how different in the follow-up video, basic wave polarization, blank polarization. I have to say blank, otherwise it gives away the surprise.
I await to be surprised.